All right. What's good, everybody? Thank you guys so much for joining us with another live stream with Algebra 1 with Mr. Peters. Today, we're going to be talking about how to simplify radical expressions. So, we're going to do an overview and we're going to touch on 5 major topics. We're going to talk about how to simplify radicals, how to simplify radicals with variables, how to add and subtract radicals, how to multiply and distribute radicals, and then we're going to end this video off with how to rationalize radicals. So we really hope you find value in this video, and we hope you stay till the end of this video because this is going to be a very important topic that you will see in Algebra 1. So let's start off. When we're talking about radicals, the whole idea is that we want to use square roots and perfect squares to basically divide larger radicals. So this is what I mean. So we have radical 4, it's a perfect square root, which is 2. Then we have 3 times 3, which is 9. That's also another perfect square. We have 16, which square root is 4. Then we have 25, whose square root is 5. And we could go on and on. But typically what I tell students is this. We're going to try to divide using the largest perfect square. So anytime you have a radical, use your perfect squares to divide. So when we look at these, I know that 5 can't go into 24. 16 can't go into 24. 9 can't go into 24, but 4 can. So if I broke this radical down, I could break this down as 4 multiplied by 6. Now at this step, anytime we have a perfect square, we take its square root. So 4 simplifies, it comes out the radical, and we have the square root, which is just 2. And because there's no perfect square that we could divide 6 by and get a whole number, it stays under the radical, and this would be our answer. Now, let's say we were talking about cube roots. And that's another reason why this video is going to be helpful, because we're going to touch on cube roots. I know teachers normally don't spend too much time on those. But let's say we had the cube root of, let's see, what's this problem? 27. So what we need to know, and I only know like the first cubes, right? These are like the most common. So we had the cube root of 8, which is equal to 2 times 2 times 2. As you see, cube roots, you multiply one number by itself twice. Now the next perfect cube is going to be 27, which is equal to 3 times 3 times 3. So cube root of 8 is 2, cube root of 27 is 3. Now if we do the cube root of, let's see, 64, that's going to give us 4 because it's 4 times 4 times 4. And then the last one for the day, the cube root, I believe, of 125 is equal to 5 times 5 times 5. So this knowing those most common perfect cubes is how we're going to break these down. So if they ask me for the cube root of 27, basically what they're saying to me is, right, we can just put the answer of 3 because it's a perfect cube. Now that we got that down, we're going to jump into some practice problems. And with this video, we're going to do a lot of practice problems just so you guys have extra practice problems since it's a live stream. All right, so let's write these practice problems out. Okay, so let's do 3 at a time. So we have 150, that's problem 1. We have 4 times radical 144. And then the last one, we have 2 times radical 112. Now, the way that I approach these is I think about all my perfect squares. So let's start off with like 100, right? We know the square root is 10. 10 times 15 probably, or 100 actually can't go into 150, I'm sorry. So we can't use that. Then we go down, we say, hey, can 64, right, go into it? No. I go under, what about 49? No. So when I go all the way down, I notice that the largest perfect square that goes into 150 is 25. And we multiply 25 times 6 to get this radical 150. Now to simplify, I look at both of my numbers. This is the only perfect square. Square root is 5. It's on the outside of the radical. And because we can't break this down, it stays the same. Right? 5 radical 6, that's our final answer. Now, in other instances, when we have a perfect square and we simplify, we just take the square root out. And if there's a number on the outside, we multiply. So right here, this is what happens. We have 4 times the square root of 144. So this is a perfect square. This turns into 12. So after we multiply 4 and 12, we're going to get 48 as a final answer for problem number 2. But problem 3 is going to be a better example of how we multiply after simplifying, okay? So when we look at this one, let's say I go through my perfect square. So I have 112 divided by 64, right? That doesn't work. I do 112 divided by 36. That doesn't work. Every time I'm going through this process, guys, I'm trying to divide using only perfect squares first. So let's try 112 divided by 16. All right, so that's a match. So now we have 16 times 7 when we break this radical down. And when I look at both of these numbers, this is the only perfect square. We take it out, and now we have 2 multiplied by the square root of 16, which is 4, multiplied by radical 7. Sometimes students will make a mistake, and they will add this number and the square root of what's under the radical. Just remember that we are multiplying, okay? So now at this step, this turns into 8 radical 7 as a final answer for us. Now, before we finish this first section of the video, we're going to now touch on some cube roots as well. And if anybody has any questions, we're going to try to pay attention to the chat. But if we're not able to get your question, we do apologize. All right, so we go to our cube roots, right? And we're going to do 2 examples. So we have 2 times the cube root of 54. And then in our second example, we have the cube root of 24. So none of these are perfect cubes. So that's really good. So when we break this down, right, I know that, let's see, I don't believe, let's see, 8 does not go into 54. No, right? That's the first cube. The next cube is 27. I know that we could take the cube root of 27 multiplied by 2 to get the cube root of 54. Now, when I look at both these numbers, this is the only perfect cube, and its cube root is 3. So this turns into 2 times 3 times the cube root of what's left under the radical, which is 2. So when we simplify by multiplying these two outside numbers, we're going to have 6 times the cube root of 2 as a final answer, and that is correct. Now, problem number 2, we obviously can't use 27 because 27 is much larger than 24. Can't divide 24 by 27. So I'm going to automatically use 8. So I go in and I say, okay, hey, the cube root of 8 times what? 3, right? 8 times 3 gives me 24. So now I broke it down and I'm looking and I say, hey, here's my cube root. All right, I simplify the cube root. We know the cube root of 8 is 2. So the final answer will be 2 times the cube root of 3. We know 3 stays under the radical because, right, it's not a perfect cube. We can't break it down. So this is the first aspect of our video, just regular simplifying radicals, cube roots. Now in the second part of our video, we're now moving on to simplifying with variables. And before we get there, we need to understand this important concept. Right? So when we're talking about simplifying x squared, the square root of x squared is just x, okay? And when we apply this to larger exponents, what we have to understand is that every pair that we get is going to be a perfect square, right? So, matter of fact, let's do it like this. We know x squared is equal to x. So I could break x to the fourth down as x squared multiplied by x squared. Now, when you take the square root of the first x squared, this is equal to x. And then when you take the square root of the next x squared, that's equal to x. So as we simplify, right, we now have to multiply our answer, and this is equal to x to the second power. So what I tell students is for the square roots, but we're basically dividing our exponent by its root, and we know the root is 2 when we do not see a number. So when we get into examples, I'm going to explain this more, and I really hope that this makes it easier. So let's look at our first example. And we could do some erasing. Let's erase. Yeah, let's leave this up here and switch colors. So our first example, we have 16, radical 16x to the second power. So even though it's variables, guys, it follows the same exact format, right? So when we look at this, right, this is saying we have 4 times x times x. Anytime you multiply by the same number, same variable, this is the square root, right? Multiplying by the same number. So the square root of 16 is 4, and the square root of x squared is just x. This right here is just a breakdown so you can visualize it under the radical. So if we're simplifying radical 16x squared, this would be our answer. Now in our second example, let's say we had a larger one. So now we have 25 x to the 6th power, y to the 12th. So when we think about this, right, this could break down to 5 times x squared times x squared times x squared. Another way I try to explain this to students with variables, right, under the radical is think about multiples of 2. So 2, 4, 6, 8. When you split it up like that, every x squared you get counts as just x once you simplify it from under the radical. Same thing with y to the 12th, right? So I have y squared times y squared times y squared times y squared. So the reason I did it like this is so you guys could see. So 5 times 5, that's 1 pair, right? So we know the square root of 25 is 5. When we talk about x, how many pairs of x do we have? 1, 2, 3. X to the 3rd power. Like I said, if you have even exponents and you divide by 2, right? 6 divided by 2 gives us x to the 3rd. That's how I like to teach it to make it simple. Because drawing it out like this is going to take too much time. Now, when we get to y, obviously the answer is y to the 6, because when we divide our exponent by the root 2, we get 6. And even when we draw it out, we have 1, 2, 3, 4, 5, 6 pairs of y squared, right? So that's why we have y to the 6. So what we're going to do now is do some more practice problems, and hopefully that explanation kind of simplified it for you. And yes, I'm going to touch on when the exponents are odd because it is a different way that we solve. All right, so let's erase this. All right, so let's see our next 2 examples. Let's write those out. Okay. All right. So another reason I like to say multiples of 2 is because when we start splitting the radical, it's much easier for us to simplify with odd exponents. And I'm going to show you what I mean. So let's say we sped up the process, right? I know that when we break this down, right? Oh, goodness, I messed up my whole radical. So when we break this down, this is going to be 5 times 5 times x to the 6th power. All right, you know what? Let's do it like this. I'm sorry. Just to make it simple. So we have 5 squared times x to the 6 times y to the 12th times y to the 1st. The reason that we do this, guys, when we focus right here, when we multiply when we multiply the same base, y is the base, and they have exponents, we add them. So y to the 12th plus y to the 1st is equal to y to the 13th. Now, I wrote it like this because when we simplify, it's easier. I have a pair of 5s, right? So when we simplify this is the same thing. Square root of 25 is the same thing as the square root of 5 squared. So we know 5 comes out of the radical because 25 is a perfect square. X to the 6 turns into x to the 3rd, right? We're dividing those exponents. See how many pairs of 2 we could get from x to the 6. Then y to the 12th turns into y to the 6. And that lone or that odd exponent now just stays under the radical by itself. So what I want you to do is pause the video or even go back to the last example when this was an exponent of 12. This is the difference between those two problems, just that last y being under the radical. Now, when we go over to our second example now, let's break this down. So what we're going to have here is 2 times 4 times 10, right? So when we think about the perfect squares that go into 40, 25 can't go into 40, right? We know its square root is 5. 16 can't go into 40. 9 can't go into 40, but 4 can. So we have 4 times 10. And if I follow that rule of multiples of 2, I'm going to have a to the 18th, because that's the highest even number before 19th. And we're going to put that a to the first power by itself. Now, when I simplify, 2 stays on the outside, and we're multiplying that times the square root of 4, which is 2. 10 is going to stay under the radical, so I'll just circle it. Or you can leave it alone, whatever helps you to remember. A to the 18th, right, now turns into a to the 9th, and a to the first stays under the radical. So what's left under the radical is 10a. So we clean this up. 2 times 2 gives us 4. We have a to the 9th, followed by radical 10a, and this would be our final answer. Now, before we go on to the next section of adding and subtracting radicals, I'm going to touch on one cube root example of how to simplify. All right, so let's erase this. And as we're going through these problems, guys, say if you didn't join us for the live stream, you're re-watching this, please make sure that you pause the video, try some of these problems, see where you messed up at, and then resume the video and see what you could have done to solve properly. So when we go on to our next example now, let's do the same thing. So we know the cube root of x to the third is equal to x, right? Because we have x times x times x. So the cube root of this is just x, right? Now if our exponent is higher, meaning we have the cube root of x to the 6. So now we're saying to ourselves, how many pairs of 3 are in this radical? And when we look, that was a horrible bracket. It's supposed to look like this. I don't know what I just did. Just I'm sorry about that, guys, but all right, let's keep going. So here goes our first x to the third. So this is x, right? Comes out of the radical, and here's our second one. So we know the cube root of x to the 6th power is just x times x, which is x squared. Now let's say we bring in the odd exponent example, right? So now I got the cube root of x to the 7th power. If we follow that multiples of 2 principle, but we say 3, let's think about it. We have 3, 6, 9. So 6 is a multiple of 3. So the way I want to break this down is the cube root of x to the 6th power times x to the 1st. I know x to the 6 is equal to x squared, right? So when this comes out of the radical, it's going to turn into x to the 2nd power, and x to the 1st stays under it as just x. So this would be my final answer if we were breaking down the cube root of x to the 7th. Now that we understand that concept, we're going to go into our one practice problem on simplifying cube roots with variables. All right, let's get it going. And like I said, guys, thank you for joining us. We love doing this for you guys. It is so much fun. And we thank you guys for the support and the comments, the likes, the shares, everything. We would not be a channel without you guys. Thank you. All right, so our example now, we have 2 times the cube root of 40 w to the 16th power. Okay, so let's break this down. Luckily for us, we just did 40, right? But it was a square root, right? Now we're talking about cube root, but it's cool. 8 times 5 gives us 40. We know 8's a perfect cube. Now, when we get to w to the 16th, we're talking about multiples of 3 now because we're talking cube roots. So we're going to multiply this and split w to the 16th as w to the 15th times w to the 1st. And you don't have to put the first. You could just put w. There's an understood one. I'm just doing that so you guys understand for the video's sake. Now we go under, we were going to simplify. So we have 2 on the outside multiplied by the cube root of 8, which is 2. There is no cube root of 5, so it's going to stay under the radical. The cube root of w to the 5th. So how many pairs of 3 are in 15? So when we divide 15 by 3, we're going to get w to the 5th. And w, oops, cross this out, my bad. And w to the 1st, there is no cube root for it, so it'll stay under the radical. So when we start cleaning this up, right, we're going to have 4w to the 5th power times the cube root of 5w. And let's double check our notes. Yep, that's absolutely correct. Now we're done with that first aspect of the video. And now what we're going to do is move on to adding and subtracting radicals. So there are two very important rules when we're talking about adding and subtracting radicals, okay? So let's write these examples out. All right, so there's three instances. So rule number one, and I need you guys to make sure you listen clearly because I'm here to make this easy. Number one, for us to add radicals, there's two of the most important things. They have to have the same number under the radical, and they have to have the same index slash root. So what do I mean? Same number under the radical. There's no number in the root, so we know it's 2. Same number under the radical, that's the first condition, right? Second condition is same root, right? Radical 7 plus radical 7 gives us 2 radical 7. The radicals act as variables, okay? They're not going to change. You're not adding the actual 7 with 7. You're just adding, hey, there's one radical 7 here and another, so that means we have 2 radical 7. So in this problem, no, we could not add because they're not the same number under the radical. And when we get down to our third example, right, we cannot combine this because this has a index or root, same thing, of 2, and this has one of 3. No, different indexes. So this is what I mean when I said they have to have the same number under the radical and the same root. So we couldn't do this problem because of different roots. Couldn't do this problem because there are different numbers under the radical. And this one we could do because they meet both those conditions. So now let's get into some practice problems. All right, so let's write like 2 of these out at a time. So here goes problem 1. We have radical 12 plus radical 75. It's problem 1. And in problem 2, we have 6 radical 60 minus 3 radical 15. All right. So as we see, guys, the most important thing is that both of these roots are 2, right? It's assumed because there's no number in the index. So that means we can add them once we break them down. Most of these problems you're going to get, they're not going to be broken down. You have to break it down to see if we can add. Sometimes you can't add. So let's look at this, right? When we look at 12, the largest perfect square that goes into it is 4. 9 cannot go into 12. So I have 4 times 3. When we simplify more, meaning take the square root of 4, this turns into 2 radical 3. Now I go over to my next radical, and I know, let's see, 36 can't go into 75, 49 can't go into 75, but 25 can. So what times 25 gives me 75? 3. Now we take the square root of 25, which is 5. There's no square root for 3, so it stays under the radical. And now once we add, we just combine our coefficients, right? 2 plus 5 gives me 7. Final answer is 7 radical 3. Now in our second example, this is a little bit different because after we simplify, we're going to have to do some multiplication. And sometimes students confuse this step because of adding and subtracting radicals. Even though we're adding and subtracting, if a perfect square comes from under the radical, we multiply. And I'm going to show you in this example. So we have 6 times, and when we break down the radical 60, this is going to be Let me check my notes one more time. I forgot, guys. I'm sorry. Okay, there it goes. I know it was 15, but I forgot what times 15. 4 times 15, right? And then we're going to bring down 3 radical 15. We can't break down radical 15 no more, guys. There's no perfect squares that go into it, okay? So now we simplify 4. This turns into 6 multiplied by the square root of 4, which is 2, multiplied by radical 15. The rest of the problem stays the same. Now we clean this up, 12 radical 15. And once we subtract 3 radical 15, this is going to turn into 9 radical 15. So when we're talking about adding and subtracting radicals, this can be misleading because of the adding and subtracting. But when you simplify, you're still going to multiply the outside number and the square root from whatever comes from under the radical, okay? Now what we're going to do, we're going to move on to one more example, and then I'm going to go over to cube roots and adding and subtracting with variables. I'm touching every topic for you guys. This is going to be one of the best radical reviews I've done on my channel and that you guys have seen. So let's go to this problem now. And I want to do this problem because this is what you're typically going to see. And honestly, students get this wrong because they're just doing too many steps at one time. So this is what I'm going to do. Instead of simplifying radicals, simplifying, one after the other, I'm going to do one completely, then go to the next one, then go to the next one. And like I said, guys, you could do it whichever way you want. So when we break down the first one, we have 2 times radical 4 times 2, right? We break 4 down, square root is 2. The other radical 2 stays under. So when we break down our first radical, it's going to turn into 4 radical 2, right? So let's just underline this because this is done. There's nothing else we could do with it. Now in the second one, we have 4 times radical 96. So when I take my calculator, I divide by 36. 36 doesn't go into it. So I go down lower. 25 doesn't go into it. I say 96 divided by 16. That goes into it. So now we have 16 multiplied, I believe it's 6, yes, right? And at this step, we have to continue simplifying. So I take the square root of 16, which is 4. So now I have this outside 4 multiplied by the square root of 16, which is 4, multiplied by radical 6. When we go to the last step, this is going to turn into 16 radical 6. Now you guys are looking and saying, hey, Peters, we have a radical 2 and a radical 6. That means we can't add those. You are absolutely correct. You're absolutely correct. And then we go to the last one, which is 24. And by now we know that this is 4 times 6. When we simplify and take the square root of 4, this turns into 2 radical 6. We're going to bring it down because there's nothing further for us to do. Now at this step, this stays the same. So our final answer will be 4 radical 2. And then we're going to do 16 minus 2, which gives us positive 14. And we can't forget our radical 6. So typically when we're adding and subtracting radicals, this is what you're going to see. They're going to give you 2 to 3 radicals to add, and not all of them you're going to be able to combine, okay? All right. So now we're going to go over to our variables example. We're only doing one example because most of the time they don't give you variables under the radical, but I want you to know it's the same exact thing. Nothing changes. $98. Is this x or x squared? Let's make sure. Okay, x. Okay. So now let's look at this. So first off, we should know off rip that the x's are going to be under the radical because we cannot take the square root of just x. It needs to at least be x squared. So that's something we need to notice. So the numbers, nothing changes. When we talk about 32, we're going to have 16 times 2 times radical x. Perfect square 16 comes out. So we have 5 multiplied by 4 multiplied by 2 multiplied by radical 2x, right? We know we can't simplify that. And then when we finalize this is 20 radical 2x. So we're done with the very first radical. Now we go to the second one, 98x. So when we break down 98, let me see, what did I use? Oh yeah, we have 49 multiplied by 2 multiplied by x. So the same thing occurs. We could take the square root of 49. So this turns into 4 multiplied by 7 multiplied by radical 2x. No, we can't simplify that anymore. Simplify again by multiplying those two outside numbers. We have 28 radical 2x. And now that we have the same number under the radical, we just add 20 and 28 to get 48 radical 2x. And that is our answer. Now, just for video's sake, let's say that this was x squared. The only difference this would make is now the x squared would came out with the outside number as just x when it's simplified. Hopefully you guys are with me when I explain that, okay? And now we're going to go on to a cube root problem. And I really hope you enjoy this problem because like I said, I know teachers don't always do cube roots. And you definitely see it on SAT, ACT test. Wanted to make sure I touch it. So we have the cube root of 16 minus 4 times the cube root of 54 minus the cube root of 128. So when we think about this, guys, let's break this down. All right, so we have 3 times the cube root. And what could we divide 16 by? 8 times 2, 4 times 4. 4 times 4, there are no perfect cubes. So we would rather use 8 times 2, right? 8 multiplied by 2. Now, when we simplify even further, here's my perfect cube. It comes out as 2. We know we're multiplying that with 3 because that's what's on the outside. And then what's left over is the cube root of 2. When we finalize this, it's going to be 6 times the cube root of 2. So that's the first one. Now, let's go to the middle. So when I go to my middle radical, we have 4 times the cube root. And I want to say this one is 27. Let's see. 27 multiplied by 2 is 54. So anytime you're trying to guess what numbers to divide by, guys, use those perfect cubes and perfect squares I talked about in the beginning of the video. You're going to be constantly and repeatedly dividing by the same perfect squares, okay? And perfect cubes. So now I have the cube root of 27 multiplied by the cube root of 2. There's only one perfect cube here, which is 27. So we have minus 4 times the cube root of 27, which is 3, times the cube root of radical 2. Now when we simplify, this is minus 12 times the cube root of 2. And right now we notice that these have the same number under the radical. So we definitely are going to be able to add and subtract. All right. And then the last one, the cube root of 128. What do we break this down as? So let's go back to our paper. So let's say 128 divided by 27. That doesn't work. Let's go a little higher. 128 divided by 64. That's 2. So now I go in and I say, hey, the cube root of 64 times the cube root of 2 gives me the cube root of 128. Perfect cube right here. We're going to cross it out. This turns into what? 4 times the cube root of 2. All right. 64 is a perfect cube. We're going to bring it down one more time because there's nothing else for us to do. Now that we had the cube root of 3, right? Oh, I'm sorry, the cube root of 2, remember? Now all we're going to do to combine is add and subtract. So once we do, let's make sure I did this right. Yes, I did. 6 minus 12 gives me negative 6. Negative 6 minus 4 is going to give me negative 10 negative 10 times the cube root of radical 2. And this should be my final answer. Now, we're done with the adding and subtracting part. And like I said, I know this video has been long. I'm sorry about it, but we have to get this review. Now we're going to go over to multiplying and distributing radicals. All right, so let's do this. And before we start, let me just take a quick sip of water. Whew, sorry about that, guys. All right, so when we get into multiplying radicals, the rules are a little bit different. So there's just one major rule, and that's just that the index has to be the same, okay? The numbers under the radical do not have to be the same. So when we look at example number 1, let's just start off with blue. We could do this operation, right? We have the same root index, same thing, which is just 2. So radical 2 times radical 3 is radical 6. We cannot break it down anymore. In this second example, we cannot multiply those, right? Because they do not have the same index. We have a cube root and a square root. So that's the biggest thing that we have to understand when we are talking about multiplying and dividing radicals. So let's go through and simplify, right? Oops, I'm sorry, wrong problem. What's the problem? Okay, here it goes. So in our first example, we have radical 3 times radical 4. And there's two ways you could do this. You could multiply first, then simplify, or you could simplify, multiply, simplify. What do I mean? I got you. So if we just multiply first, right? They have the same root. It's a square root, right? Root of 2. We multiply, we get radical 12. Now, after you multiply, you always check to see if you can simplify. Yes, we can. This turns into 4 times 3. Radical 4 times 3, we have a perfect square. This comes out as 2. 3 does not have a perfect square, or we can't break it down with another perfect square, so it stays the same. Now let's backtrack, right? Let's say I simplified from the beginning, right? So we have radical 3 times radical 4. Let's say I just turn this into its square root. We'd add radical 3 times 2, which will equal to 2 radical 3. That's why I say, hey, you could multiply first, get your answer, then simplify, or you could simplify first, right? We simplify to get here, then multiply and check again to see if you could simplify. It's whatever you want to do. I only recommend the second option if we're working with large numbers, okay? All right, so we got the introduction down. Now let's go through some practice problems. We got about 2 to 3 practice problems on this section. I tried not to keep it too long for you guys because I know this video is long. All right, so let's go to this example. So we have radical 8 multiplied by negative 3 radical 2. So I'm only going to do one method for now. I'm not going to do two. So we could, let's just say we multiply straight across. When we multiply radicals, we multiply coefficients with coefficients, radicals with radicals, sorry. So what do I mean? When we multiply this together, we're really only multiplying the radicals. Negative 3 stays the same because there's no number in front of the first radical. So we have negative 3 times radical 16. Now radical 16 is a perfect square. So when we break this down, it turns into negative 3 times 4, which is going to be negative 12. And that is our final answer. Now in problem number 2, right, let's write down problem 2 and 3. So we have 4 radical 14 multiplied by 2 radical 8. So in this step, before I multiply, what I want to do, I'm going to break this down. So we go here, we have 2 times radical 4 times 2. Perfect square comes out, turns into 2 times 2 times radical 2. So we have 4 radical 2 once we break this first radical down. Other one stays the same. So let's bring it down. Right? Now when we multiply, I'm only multiplying 4 and 4 to get 16, and radical 14 with radical 2 to get radical 28. Now after I multiply, guys, remember, we have a perfect square of 4 that goes into 28. So we have to check if we could break this down, and we can. So now I break this down, and hopefully you guys can still see this. This turns into 16 times radical 4 times 7. Perfect square comes out. This turns into 16 times the square root of 4, which is 2, times radical 7. And our final answer, let's check the work. Yep, is 32 radical 7. So this is what we're talking about when we're talking about multiplying and multiplying and basically distributing radicals. We're now going to look at a variable example and then touch on the distributing aspect. Sorry about that, tongue twister. All right. Okay, so let's try this one out. Okay, so this one's going to be a little bit different. And just to make sure, let's multiply 20 times 15. That is 300. So once we multiply, we're going to have 3 times radical 300. This is supposed to be x, guys. I'm sorry, I made a typo. Yeah, that's supposed to be x. 300 x squared. Now, when we break this down, right, we're going to have 3 times 100 times 3 times x squared. Now, when we go one step further, this turns into 3 multiplied by the square root of 100, which is 10, multiplied. No, we cannot break down radical 3. X squared turns into x, and like I said, radical 3 is at the end. So when we simplify again, we'll have 30x times radical 3. Let's double check the work. Yes, that's correct. And this will be our final answer. Now we could go over to distributing with radicals. And distributing with radicals, I have a very, very important problem that I have to touch on for this video. So please make sure you guys stick around. Like I said, if you have any questions, type it in the comment box for us. Or if you want to email us, you can email us as well. I really hope you guys enjoying the show. Smash the like button for us. Oh, man. All right, drop my markers. Pick that up. All right. So when we're talking about distributing, guys, let's look at our first example. So we have 6, and on the inside of the parentheses, I'm sorry, we have 7 radical 3 plus 6. So when we go to distribute, guys, remember, we multiply the coefficient with coefficient, radicals with radicals. So when I multiply 6 times 7 radical 3 stays the same, okay? Nothing changes. So this just turns into, let me double check. Oh, I'm sorry, guys, I wrote this wrong. So let's backtrack. That's on me. Peter wrote it wrong. That's why you gotta double check your work. So now this is backwards. I'm going to multiply radical 6 with 7 radical 3. But the only thing I'm actually multiplying are the 2 radicals. So 7 stays the same, and radical 6 times 3 gives me radical 18. Now, when I go back and distribute, meaning I multiply radical 6 by the other term in the parentheses, 6, this just turns into 6 radical 6. Okay? That's how we combine a radical with a non-radical. Okay, we multiply radicals with radicals, coefficient with coefficients. So here I could simplify, right? This turns into 9 times 2. 9 is a perfect square. It's going to come out as 3. So we have 7 times 3 times radical 2. And this is going to stay the same because there's no perfect square that we could break 6 down with. So we'll bring it all the way down to the bottom as 6 radical 6. Now when I clean this problem up, final answer is 21 radical 2 plus 6 radical 6. Let's double check the work, and that is absolutely correct. Now in our second example, let's switch to black because I'm not going to erase yet. We have 3 radical 2 as our term. And then on the inside, what we're going to have is 5 radical 10 minus 2 radical 6. So this is going to highlight what I meant when I said, hey, we multiply radicals with radicals, coefficients with coefficients. So when I multiply 3 radical 2 times 5 radical 10, I'm multiplying 3 and 5 to get 15, radical 2 and 10 to get radical 20. Now when I go back and do the same thing, meaning I distribute 3 radical 2 to negative 2 radical 6, 3 times negative 2 gives me negative 6. And 2 radical 2 times radical 6 gives me radical 12. So now we've distributed. I checked my work. I do have the correct answers. Now we're going to check to see if we could break down anything, and we can. So we break down the first radical. We have 15 times radical 4 times 5. 4 is a perfect square. So now this turns into 15 times the square root of 4, which is 2, times radical 5. Final answer is 30 radical 5. Now in the second part of this example, right, we notice that we're going to have 6 times radical 4 times 3. Perfect square is 4. It comes out as 6 times 2 times radical 3. And right here, we're going to have negative 12 radical 3. Let's check my work. This is correct. Now, when I was in algebra in high school, many, many generations ago, let me stop playing. But when I was in high school, this was challenging for me because I felt like I always had to add at the end. Sometimes, guys, that's not the case, okay? And with that being said, we're going to move on to the very last example of radicals. Please make sure you guys stick around because you don't want to miss this part, please. It's the most important distributed part. All right. So we get to this very last part, and I have to touch on this because students will make a very small mistake and get this wrong. So when you see this does not mean you just square both terms, meaning, hey, radical 7 times radical 7 gives me 49. 3 squared gives me 9. I simplify to get 7 plus 9, which is equal to what, 16? No, this is wrong, okay? And I'm going to show you why. When you see a binomial, right, it's a basically expression with two terms, 1, 2, we expand it, meaning we write it twice. So what they're telling you to do is take radical 7 plus 3 and multiply it by itself. So here goes the first one, and then here goes the second one, right? Because it's set to the second power. This is what it's basically saying. So we're going to distribute now. So what that is, we have radical 7 with radical 7. We know that when we multiply radical by itself, it's just a number without the radical, right? So we'll do 7 times 7 to get radical 49. It's a perfect square. It would change back into 7. So when you see this, to cut out all those extra steps, just put the same number without the radical. So we have 7. Then we do radical 7 times 3, which is just plus 3 radical 7. Now I switch to blue just to make this stick out because we distributed 7. We multiply by both the terms in the opposite parentheses. Now we move to the second term and do the same thing. 3 times radical 7 is just 3 radical 7, right? And then 3 times 3 is going to be 9. And this is that concept where we talk about FOIL, right? First, outer, inner, last. All right. So this is the example of FOIL. I like to use the box method because it's just more easier. So now we combine like terms. 9 plus 7 gives me 16. And remember, we have two radicals with the same number under it, same index. So we just add the numbers in front. 3 plus 3 gives me 6. And radical 7 is attached at the end. So 16 plus 6 radical 7 would be our final answer. So with this being said, we're now going to move on to the very last aspect of our live stream, which is rationalizing the denominator. So when you hear rationalize the denominator, guys, you should know that we're going to have basically fractions that have radicals. And I'm going to show you a few different examples. We got probably about 5 or 6 examples, but they're going to be quick. So hopefully you stick around, and we thank you so much for joining us today on our live stream. So the first one is where they put the square root over the whole entire problem. All right. And typically with this, if you could simplify, you will simplify where possible. So luckily for us, both of these are perfect squares. So the square root of 36 is 6. Square root of 100 is 10. We could simplify this fraction more by dividing by 2 to get 3 over 5. So that's problem number 1. Now, another thing you're going to see is that they'll split the radicals. You have one radical like this, 96, divided by radical 3. And guys, just remember that the index has to be the same, okay? Meaning they both have to have a 3, both would have a 3, or both have 2. Index have to be the same for us to divide. Now, when we do this, there's what we could do is actually divide to get radical 32. Then we could simplify. What do I mean? Let's break this down as 16 multiplied by 2. When we break this down even further, we're going to get 4 radical 2 as a final answer, and that is correct. Now you're saying to me, all right, Peters, they're not going to give me all these problems where it's just going to divide evenly or be perfect squares. And guys, you 100% correct. I'm not going to sit here and lie to you. This is just the foundation so you guys understand what's going on. Now, what's going to happen is you're going to get a problem like this. Oops. I thought I took out the black marker. Sorry, guys. And let's write a few examples so you don't have to keep looking down at this paper. Okay. So we have example number 1, radical 7 divided by radical 2. And example number 2, we have 5 divided by 6 radical 2. So when you have a problem like this where you cannot divide and get a whole number, we're going to rationalize the denominator. What does that mean? We're going to get rid of it. So I'm going to multiply the bottom by that same radical, the denominator, and I'm going to do the same thing in the bottom as I do in the, I'm going to do the same thing in the top of the fraction, as I do in the bottom. So now rationalize, I'm getting rid of the radical, and I multiply the radical by itself. I got to do it on the top. Sorry about the tongue twister, but I got to make sure that you guys get this in the clearest and easiest manner. So as a result, we multiply the top. We're going to get 14, radical 14 over radical 4. Now just remember, guys, I told you a trick. When you multiply the same radical by itself, it's just that number without the radical. So let's skip this step, right? We know it's going to simplify the 2, but let's just say we knew this step. Bam. And that's going to be our final answer. Even though we can divide 14 by 2, we cannot do it in this operation because one is a radical, one isn't. So this is our final answer. Now in problem number 2, it becomes a little bit more complicated because we have a coefficient on the outside of that radical, but it doesn't change. So again, we're multiplying or getting rid of the radical. So we're going to multiply the bottom and the top of this fraction by the radical, which is radical 2. So what happens is in the top, this turns into 5 radical 2 divided by 6 multiplied by 2. Because once we multiply radical 2 and radical 2, it's just itself without the radical. So my final answer is 5 radical 2 divided by 12. Now, what I want to do is let's just change this fraction a little bit because I want to show you how you could reduce. Let's say this was 6 radical 2 all over 12. We could simplify the fraction, meaning we're not going to touch the radical. We could simplify 6 and 12, right? Divided by 6, we'll get 1 radical 2 over 6, right? But we don't need to put this that 1. So we can just leave this as radical 2 over 6 if we simplify that fraction. Oh, I'm sorry, not over 6. What am I thinking? Over 2, right? Once we divide top and bottom by 6, it'll be radical 2 over 2. Ooh, it's been a long video, guys. I'm so sorry for that mistake. All right. So we got that done. All right. So now we're going to go on to our next example. Rationalize the denominator. So in our last 2 examples for today, we're going to bring in this term called the conjugate. And before I explain what it is, let's get it up on the board so you guys understand, right? So now we have, let's make sure I'm doing this right. Okay, yeah, write this problem right. 4 divided by 2 minus radical 3. So the conjugate is basically it occurs only when you have a binomial, right? And so let's backtrack because I need you guys to get this. So when we are rationalizing the denominator or we have a fraction with a radical in the bottom, right? This is when it applies. Only when we have a fraction and there's more than one term in the bottom, we're going to use the conjugate. The conjugate is just basically the same radical with the opposite operation symbol. So it's the same radical, 2 and radical 3, but now instead of that subtraction sign, it's addition. And we do this so that we could get rid of the radical, okay? So when we multiply by the conjugate, this is going to be 2 plus radical 3. And then we go in the top and we do the same thing because that's the rules of fractions, okay? So now that we did that, I'm going to show you what happens. So let's just erase this conjugate right there, right? So we multiply 2 and 2 to get 4. Then we multiply 2 and radical 3 to get plus 2 radical 3. Then we multiply negative radical 3 and positive 2 to get negative 2 radical 3. And then we know negative radical 3 times radical 3 is just going to be that same number without the radical. So we're just going to put minus 3. Now that we got that situated, guys, and matter of fact, let's just do the regular problem. Let's just put radical 9. When we do the conjugate, what we have to understand is that it's always going to cancel out the middle term. So this middle term is gone, just like the difference of squares. So what we can do is just multiply the first 2, 2 and 2, and then the last 2, negative radical 3 and positive radical 3, because middle terms cancel. So 4 stays the same, and we know if we're subtracting radical 9, it's a perfect square. So it just turns into 3, and my final answer would be 1. Now we're going to move on to the very last problem of this video. We really hope you enjoyed this video and it's been helpful. And we're going to do the same exact problem, different numbers, but just go through it faster so you guys see how it can be done. All right, so last problem of the day. So we have, let's go to black. Black's gonna stick out a lot more. Okay. So we have radical 2 all over 3 radical 5 plus 3. So we notice that we have a radical in the bottom, right? We have a fraction, radical in the bottom. So we have to rationalize it. When it's a binomial, we rationalize by multiplying by the conjugate. The conjugate is just the same exact binomial with the opposite operation symbol. So what we do in the bottom, we have to do in the top, right? 3 radical 5 minus 3. Now, let's go to the top and let's do our multiplication. So we have 2 times 3 radical 5. So this is going to be 3 radical 10. We only multiply the radicals. And then radical 2 times negative 3, which will be negative 3 radical 2. Let me check my notes. Yep, that is absolutely correct. Now we go to the conjugate down in the bottom. And remember, middle term's going to cancel. So I'm just going to multiply 3 radical 5 with 3 radical 5 and positive 3 with negative 3. And we'll get the same. We're going to get the correct answer, I should say. So once we do this, 3 times 3 gives me 9. Radical 5 and radical 5, that's going to give me 25. But when we break it down, it's going to turn back into the square root of 25, which is 5. So let's just put 9 times 5. And then we're going to have positive 3 times negative 3, which is negative 9. So now at this step, I'm going to simplify. So we have 3 radical 10 minus 3 radical 2 all over 45 minus 9. Now, remember, we can't do anything in the top because this is subtraction. When it's subtraction and addition, we only could subtract if they had the same number under the radical and the same index. They had the same index, but not the same number under the radical. So 3 radical 10 stays the same, negative 3 radical 2 stays the same, and then 45 minus 9 is what, 36, right? Yeah, 36. Now at this step, for all my fraction haters, remember, we can simplify and always check to see if you can. 3, negative 3, 36. If we divide all of this by 3, right, we're just going to have radical 10, because we don't need to put the 1 in front. minus radical 2, and then 36 divided by 3 is going to give me 12. So this would be my final answer. And with that being said, guys, we have completed our radicals review. We really hope that this video was helpful for you guys. We hope that you found it helpful. We know it's an hour long and it's been a real long video, but thank you guys so much for the support. Leave any comments for future videos you guys would like to see on our channel. Smash the like button for us, subscribe, and if there's questions from this video, email us, comment on this video. We'll definitely get back to you. But thank you guys so much for joining us on our live stream with Algebra with Mr. Peters. Thank you again.